Define the word pressure, and pressure is a measure of how much force is applied over a given area. Okay, so we're seeing here we have force over area. And a simple example to think about is if you stand on both your feet, the force of your body or the weight of your body is displaced over both of your shoes. But the minute you stand on one foot, you feel like it's more difficult to stand because you're cutting your area in half when you lift up one of your feet. If you cut this in half, as a result, you're doubling your pressure because these are inversely related to each other. The units of force are newtons, the units of area are meters squared, so the units we have for this are called pascals. Pascals are named after the French mathematician, physicist, inventor, and writer, and philosopher. Wow, he was a Renaissance man here. His name was Blaise Pascal. Now let's talk about atmospheric pressure and what that means. If you think about it, the atmosphere around you is really a gas. So as a result, it's a fluid. So the air around you is really pushing down on you. Okay, there's a force from the weight of the air pushing down on you. Now the pressure of the atmosphere at sea level is around 10 to the 5th pascals. Okay, 10 to the 5th pascals. Or what we used to call, or what we like to call, 1 atmosphere, ATM. Now this is just another unit. So pascals and atmospheres are just units like centimeters and inches. Now the other units as well, the other units that we know for pressure are PSI, which is pounds per square inch, and then usually millimeters of mercury, also known as torr, T-O-R-R. Now the atmospheric pressure, remember, is like what's really weighing down on you or what's pushing down on the person that you see here that's slumped over. Now, Pascal's principle tells us that the pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and to the walls of that container. Okay, pressure applied equally, okay, is transmitted. Now, an example of this would be like pumping a tire. You continue to put air in the tire, the pressure on the walls of the tire and all the molecules is consistent or the same throughout the entire fluid. Another idea is an egg. Take an egg and put it in your hand the long way and try and crush it. And make sure you apply force evenly with your fingers. What you'll notice is that the pressure on the egg is equally transmitted to the wall, so there's actually a state of equilibrium. And as a result, the egg actually won't break. The third example I like to think of is hydraulics. Hydraulics, you have closed containers of fluid, and with hydraulics, you think of like things like pistons. Now let's take a look at a clear application of hydraulics called the hydraulic lift. And what we can see here is if we apply Pascal's principle, we could say that the pressure at each location is the same. So that means the pressure here, 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 all the same. Those are all the same pressure. So let's look at the pressure at the first location and say that that's equal to the pressure at the second location. Okay, again, this is the first location here. This is the second location. This car is sitting on top of a piston, and this is a plunger on the right side that's being pushed down or pushing its piston down, raising the car up. And let's discuss how this actually works. If the pressures are the same at both locations, then we could say F1 over A1 equal F2 over A2. And as a result here, if we want to figure out what the force applied is, F1, we could solve for F1 by multiplying by A1 on both sides, or simply bringing A1 up top here. So this A1 ends up here like that instead, now it's gone. The way I'll write this is as follows. I'll write it as F1 equals A1 over A2 times F2. The reason I'm going to write it that way is to see that there's a fractional value that relates the ratio of the cross-sectional areas at each location. And what we can see here actually is that the applied force only has to be a fraction of the force that is felt upward on this car. So say the car weighs like 500 pounds and you can only apply 100 pounds of force. Well, as long as this area is 5 times this area, you're good to go. Okay, so say again, if you could only apply 100 pounds of force here, as long as the ratio of these is 1/5, and this is a 500 for the weight of the car, say it's 500 pounds, which I think would be more like 2,500 pounds, right? Whatever that value is, the ratio of the cross-sectional areas tells you the fraction of the value of the weight that you need to apply, F1, in order to lift the car up. Look at an example of this. In a hydraulic lift, we could say that a 550 Newton force is exerted, on something. So let's go ahead and draw a hydraulic lift. I always draw one piston larger than the other, so this is the smaller one on the right here. So we'll say that this area is the smaller one, 1.5 square meters. The force applied, F1, is going to be 550 newtons. Now, in order to support the weight that is placed on a 4 square meter piston, so this area 2 is 4 square meters. Now it says how much weight can the wide piston lift? Meaning, what's the maximum allowable weight of this car or this object here? So what we can do is right away write that Pascal's principle tells us P1 equals P2. The force over the area equals the force over the area. Now, in this problem though, we're looking for F2. We're trying to figure out what is the weight of this car, what is the force pushing down, meaning the weight of the car really. So if we're looking for F2, we'll move A2 up now. So we're going to have A2 over A1 times F1 equals F2. And again, I get this by moving this A2 up top and then writing A2 over A1 as a fraction. The reason I do that is so you can see something here. So let's take a look when we plug in. A2 over A1 becomes 4 over 1.5, and the force you're applying is 550 newtons. Now, the units of 4 and 1.5 are both meters squared, so those really don't matter as long as the units are the same. The units here are newtons, which makes sense because our answer is a force, which gives us newtons. So what we're going to notice is this, and this is the intriguing part. This ratio of 4 over 1.5 is actually 2.7. And we take 2.7 and multiply it by 550 newtons, and as a result, the answer is 1466.7 newtons. So the maximum allowable weight of a car that could be lifted by a 550 newton push is 1466 newtons in this case. So this value here, this multiplier, right, this multiplied by 550, this is called your mechanical advantage. This is what you're getting out of this machine. You're only putting in 550 newtons of force, but you're getting out a force much greater than that. Now the thing is that you're going to have to push down on that piston or that plunger much further distance in order to lift the car up a decent amount of distance. So say you only push down, or you push down like 3 feet, the car might only lift a few inches. So you're doing the same amount of work in the end, but over a longer distance. Very similar to what we learned with the work kinetic energy theorem. The second part of this problem just says to figure out what the pressure is on either of the pistons. Now I say either of the pistons even though the problem said each because I know that the pressure is equal on each piston. Pascal's principle told me that. So since I know F1 from the problem and I know A1 from the problem, I'll use those values. I take 550 newtons over 1.5 square meters, giving me 366.7 pascals. And if I did the same thing with P2, I would use the force I just got, which is this 1466.7, over the area of piston 2, which is 4. If I take this over this, I will also still get 366.7 pascals. Next, we'll take a look at how pressure varies with depth. So first, we have to think about the fact that the pressure felt by an object underwater is really due to the weight of the column of water above it. So for example, let's say we have a rectangular solid under the water. Okay, like this. And let's say the water level's up here. Well, there's a column of water on top of this. And that column of water is really the same shape as the solid itself. And that weight of that water is the force that's really pushing down on it. So right away we know that the pressure equals force over area, but the force felt is the weight of the fluid, which is the mass times gravity of the fluid, over the cross-sectional area. Well, the cross-sectional area is this area right here. If I consider this to be length and width, I can replace this with LW here, right? Well, take a look at this. This is mass of the fluid. Mass is really density times the volume of the fluid times gravity. Well, the volume of the fluid, turns out, if you look at this fluid now, the fluid's volume is length times width times height. Now that height is really also known as the depth below water level, right? This is really the depth below water level, also known as the height. So the volume of that fluid is LWH. So this becomes LWH. And what we'll notice that the LWs are the same LWs. The LW from the container and the LW from the column above it are the same. So those end up canceling, leaving behind rho times G times H. And that's what you always see the formula as, rho G H. Okay, again, when it's under a fluid, we'll put rho F for fluid, but it's rho GH, where H is the depth. This formula over here is really known as gauge pressure. But since the atmosphere already applies pressure, right, already applies pressure known as absolute pressure, then the total pressure at a given depth is given as the following. Pressure equals the atmospheric pressure plus rho GH. Okay, so the atmosphere plus the pressure from the fluid on top of it gives you the total pressure felt by the object. remembering that PO is atmospheric pressure, which is 1 times 10 to the 5th pascals. Example 2 says, calculate the depth in the ocean at which the pressure is 3 times atmospheric pressure. The density of seawater is 1,025 kilograms per cubic meter. Okay, 3 times. Let's put a little S right there. Now, we want to figure out what the depth is, so right away we're looking for H in this problem. We know that the pressure is triple atmospheric pressure, so 3PO. We know that the formula for pressure is P equals PO plus rho GH. Well, rho in this case is 1025. That's in kilograms per cubic meter. So I replace what I know. I know that this is really 3PO equals PO plus rho GH. Now PO and 3PO are like terms, so I subtract the PO from both sides. 3PO minus PO is 2PO, and that equals rho GH. Solving for H, we get 2 atmospheric pressures over rho G is equal to H. At this point in time, we just simply have to plug in. Okay, so 2 times atmospheric pressure all over rho, which is 1025 kilograms per cubic meter, times gravity. And as a result, we get a height, or in this case, height means depth really, right? H, or the depth of 19.9 meters. Make sure you put parentheses around your denominator when you're calculating this, because you have to divide by that entire quantity. So again, this means that if you wanted to have triple atmospheric pressure, you just have to go down about 20 meters or around 60-ish feet underwater, under salt water.